Let's activate the event. So today is day 8th of December, and we have another yet puzzle. What I see again is something with a map. Let's read it out.
You find yourselves on the roof of a top-secret Easter Bunny installation. While the historians do their thing, you take a look at the familiar huge antenna. Much to your surprise, it seems to have been reconfigured to emit a signal that makes people 0.1% more likely to buy Easter Bunny brand imitation mediocre chocolate as a Christmas gift. Unthinkable. Scanning across the city, you find that there are actually many such antennas. Each antenna is tuned to a specific frequency indicated by a single lowercase letter, uppercase letter, or digit. You create a map, your puzzle input, of these antennas. For example,
Puzzle input. Okay, so we have some again map of antennas, and
the signal only applies its nefarious effect at specific antinodes based on the resonant frequencies of the antennas. In particular, an antinode occurs at any point that is perfectly in line with two antennas of the same frequency, but only when one of the antennas is twice as far away as the other. This means that for any pair of antennas with the same frequency, there are two antinodes, one on either side of them. So, for these two antennas with frequency A, they create the two antinodes marked with null.
no. Yeah, I'm not sure I understood this one. So, what do we have here? We have A's here. Is it a completely different map? Does it supposed to, like, relate somehow? Probably not, because there are more dots than here. Yeah. So, for two antennas with frequency A, we then create two antinodes marked with, however this symbol is called, like that. I forgot actually, like a grid or hash. So, adding a third antenna with the same frequency.
Adding a third antenna with the same frequency creates several more antinodes. It would ideally add 4 antinodes, but 2 are off the right side of the map, so instead it adds only 2.
I see, so it's like, and what's the antinode? Based on resonant frequencies, an antinode occurs at any point, so they're perfectly in line with two antennas of the same frequency. But only when one of the antennas is twice as far away as the other. Alright, I see. So it's like we have a distance between antennas, and we have this antinode which is on one side, so that it gives twice as distance from the one. We take the distance between two antennas, and then we just add it up and place there this antinode. So we have here two antinodes, and the distance between those is like one dot, or we probably do this. So two nodes here this way, and one node here. The same way we go and find this point. The same way we go find this point. So that distance between the antinode and this antenna is twice the distance between the antennas. So here again we get 2 antennas. We get like on the both sides we get the same picture, but when then we add this one, this antenna, and then therefore we have this antenna there, and another one appears here as well, because again 1 1 2 3 4 1 1 2 3 4. Okay.
Antennas with different frequencies don't create antinodes. A and A count as different frequencies. However, antinodes can occur at locations that contain antennas. In this diagram, the lone antenna with frequency capital A creates no antinodes but has a lowercase a frequency antinode at its location.
Yeah, so the capital A does not produce a antinode with small a, but what? Create no antinode, but it has a lowercase a frequency antinode at its location. Yeah, but antinodes can occur at locations that contain antennas. The first example
has antennas with 2 different frequencies, so the antinodes they create look like this, plus an antinode overlapping the topmost A frequency antenna.
So we get back to the first picture. So here what we got those zeros that are actually antennas, and then we need to produce the antinodes for all of those. So we got, so for example, 1 2 3 1 1 2 3 1. So here we should have a antinode, and here it is. So the same thing for what? For example, for those we have 2 antennas. For those we have two antinodes. For those we don't. What? Why? I'm not sure. So like, probably if we place different frequencies for the antennas, like if they're placed, we got an antinode, only one antinode over there and nothing here, is it? So probably, let's see other example. If we could like do those, yeah, but we got an antenna here, so probably an antinode would be there. What else? Do you have other example? 0A only. Yeah, 1 2 3, but it's out of the map, so I can see that. Again, let's see why.
Antennas with different frequencies don't create antinodes. A and A count as different frequencies. However, antinodes can occur at locations that contain antennas. In this diagram, the lone antenna with frequency capital A creates no antinodes but has a lowercase a frequency antinode at its location.
So I'm really not sure. So we have here 2 antennas, and the antinodes of those producing one of these antinodes is here, but I don't see any, like, because they have this the distance is the same. I'm not sure if we would have a antinode contained here. I don't know. Karakalpak. Is it even a language? Sorry if I'm not going to offend anyone. So yeah, let's make AI figure it out. Probably. Yeah, so let's see the rest.
Because the topmost A frequency antenna overlaps with a zero frequency antinode, there are 14 total unique locations that contain an antinode within the bounds of the map. Calculate the impact of the signal. How many unique locations within the bounds of the map contain an antinode?
So we have a situation where the antinode can be in the same place as the antenna, and we need to figure out whether we need to count those. Probably yes, but so they are saying 14 total unique locations. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So yeah, antenna can cover the one of the antinodes. By the way, yeah, this would be pretty straightforward to visualize. I can do that. We could have some time to visualize. Yeah, we have different letters, different like numbers, 3 digits here, which will be these antinodes. So yeah, let's get our puzzle input. Is it full? 2, yeah, it is full. And let's see if AI is able to solve this one. I would give GPT-4o Mini a chance now. Let's also attach README file. And yeah. So what does it think? Potential approaches. Approach 1. Implement basic algorithm to count unique antinode locations based on a provided description. Approach 2. Create a more complex algorithm that considers positions of the antennas and calculates antinodes based on their frequencies and distances. What's the difference? Given the complexity, I will proceed to approach 2, implementing a solution that calculates unique antinode locations. Alright, solution seems pretty easy, like pretty small. So we iterate through the grid and find antennas and calculate antinodes. We go through all the points. If it's not a dot, then we get a frequency, which is just a letter that's contained in this cell. And check for other antennas of the same frequency for divide the range. What? Oh, okay. So it just goes again through all the rows and then columns. So rows and columns. If the x dy doesn't it is not equals to x and y. So if that's the same place where we first get our frequency and the letter is the same, we calculate the distance. If the distance is more than 0, yeah, we already checked if that's not a 0. Calculate antinode positions. Antinodes at x plus distance. Why do you apply only x? So the distance is only between the x, not y. From what I see, this is not a correct solution, but for the sake of it, just let's run and test. Probably not the correct answer. Yeah, too high. Yep. GPT-4o Mini wasn't be able to solve this one. Let's try it with 3.5 Haiku, Claude. So what do we have here? Problem requirements. Find endpoint for potential approaches. Brute force approach. Simple to implement. Straightforward logic. Okay. Optimized search approach. I would like to see that one. Recommended approach. Use the dictionary to track antenna locations by frequency. Iterate through for each frequency group. Calculate antinodes for each pair of antennas. Use that to track unique locations. Yeah, and here it compares the dx, the y. So it has, it's calculating the distance using both coordinates, both axes. So it's definitely more correct approach. Again, Claude just nails. So group antennas by frequency map, set default, append xy. So default value is list, and then we append x and y. Frequency map. Oh, this character. For this character that appears in the cell, if that's not a dot, we create a list that contains what just contains coordinates. Okay, see. So we create a dictionary that has different letters as a keys and all of the possible positions as a value. I like this approach. Track unique antinode locations, just creating a set. Find antinodes for each frequency group for frequency and locations in frequency map, so character and their position. Then we enumerate all of the locations. Okay, so for example, we get frequency A, and then we find all the positions of frequencies of the same frequency. We iterate through all of their positions. Then what for x and y, all locations in I+1. So we get the rest of the locations. We calculate the midpoints and the distance. A dx is just difference between x's, dy difference between y's. Middle is just divided by 2. Check if one antenna is twice as far. Absolute x equal to 2. Absolute x2 minus mid x dy equals to it's hard to comprehend this part exactly. So dx is just difference is 2. So what? Oh, just iterating through all of the locations. But shouldn't we like iterate through all of the grid, or just place the antinodes within the grid, not by checking the locations that are inside of the frequency, because it would get us just intersection, like in a where the antenna and the antinodes are located in the same place, isn't it? Let's see, 186. It's definitely smaller, so yeah, it's too low. As I thought, this just checks for the, as I understand, we should have iterated through all of the grids, or just placed all of the internodes first, and then we should just check. Here is it iterating through the rest part of the locations, or even just iterating for the frequency map, all the locations of the same frequency, and it's not the correct approach. I won't give Claude Haiku another chance. We'll try Claude 3.5 Sonnet. Let's start from GPT-4o. I wonder whether it will get it. Okay, so potential approaches. Pass the input, calculate antinodes by checking pairs of antennas with the same frequency. Okay, use a set to track unique antinode positions. No duplicates. So, what we have here, again, we append, we get our antennas. It's a list now, not a dictionary. Then we iterate through all the antennas. And then we iterate again through all the antennas, because we need to really find the distance between both. Then, if I is bigger than j, not sure why, and frequency is not frequency 2, this is the correct one. So if the frequency are not correct, even are not the same, we continue. Okay, see now. So because we're using enumerate here, we won't get the same. We don't need to compare the same antennas, and that's why we have I and j, just a row, like it's like an ID of the antenna. So if the ID is the same, we should continue. But why does it do bigger than that? So again, we're comparing the rest of them. Alright, probably correct. Dx dy we calculate, then what do? We get the remainder of dx and over 3. Why do we do that? If the remainder is equals to 0, mx, middle x, middle y, we divide them by 3. Because what? It could be a correct approach, but I'm not sure what does it do here. Probably not the correct one, because it just gives us 0. Sorry, GPT-4o. Let's try again with GPT-4o, just to see if it's just not enough for the yeah, it's just giving the same thing here, completely the same, and the answer is 0 now. Part 2, it's even tried to place part 1 and part 2. Yeah, the solution is not correct. Definitely not 0. Okay, so again, GPT-4o didn't solve this. Let's try Sonnet. I'm pretty sure Sonnet should be able to do this one. So, potential approaches, store antennas in dictionary. Yeah, I like this approach that we are storing them in dictionary and then we go only by the same frequencies. For each frequency group, calculate antinodes between each pair. Use set to track antinodes locations. Okay. So let's see. Let's firstly check if it gives us anything. Yeah, 195 could be the correct answer. No, it's too low. Sorry, Claude Sonnet. I won't go through the solution because it's not correct. Let's just give it another chance. And if the answer won't be correct now, what did it say, by the way? Too low. So 195 is too low. We need to get higher number. Distance squared is collinear. Seems like it takes time to apply this this answer. Let's do what? Why do you not proposing to apply? Okay, I will just do it myself. We finish at part 1. So what's going on here? Parse input. Part 1, grid, parse grid. Okay, you just haven't finished the answer yet. So we probably need to, like, what? Finish it. For some reason, Claude just finished, like, stopped giving us an answer. So let's, oh, okay, so it's fine. Apply. And let's see if the answer is bigger. No. Part 2. Part 1. Yeah. Alright. So none of the models was able to solve this problem. That's interesting. Okay. We'll try O1 now. And if, yeah, let's start from the O1 mini. Let's revert back. Let's place the code we have. Use this code to fill. We have input txt file with real input, and let's see what O1 mini will get us. Apparently O1 mini is like not a smart model, but because it's using this thinking approach, it could be able to solve, because Claude and GPT-4o, they're just like giving what they have memorized and not really analyzing what they are doing inside the solution. They can just not they're maybe not comparing the potential approaches correctly while writing the code, while not planning the solution, like we've seen in the cursor in the first part, the planning stage here. By the way, this is just a prompt if you wonder. why it's doing that. I have a cursor settings, and I have a rules for AI, and this is just a large prompt that it's using. Therefore, it's writing this code analysis first. But yeah, so let's try it out. No linter errors. Okay. Part 1, part 2. Let's see. Alright. So now we got something that is bigger than 195 and less than what we had, 900. It could be a correct one. So 293. 293. Yeah, 1 gold star. So, alright. So 101 Mini was able to solve this one. I like that the code is not very large, but what I'm going to do now, because I don't like really the naming they're using, I'll ask Claude 3.5 Sonnet to hi Jarvis, please make the code more readable and with better naming. Why do stop? More readable and with better. I prefer doing it with my voice to write prompts, but yeah, because I'm just tend to make a lot of typos when I write fast. So let's see if this code will give us the same answer after refactoring. Please apply it finally. And yeah, it's just the first part. It's not even the second one. We'll see what's in the second part. Could be that the problem is even harder. Probably is. Okay, it's failed to apply this. Just something is going on with cursor or with Claude today, so it's not giving us the full answer. But yeah, it's enough. Let's see if it gives us the same answer. Yeah, and let's try to understand what is going on here. Calculate the number of possible antinode positions based on antenna pair. An antinode position calculate for each pair. For each antenna pair, there are 2 possible antinode locations, position locations. At a distance 2 from B to A, a distance 2 from A to B. Alright, grid height, grid width. Antennas by frequency. We enumerate through the grid. Yep, we get character. We enumerate through all of 3. Then we get our antennas by frequency is again a dictionary. It looks like the thing that Claude gave us before. So we have a dictionary with a list of locations of the antennas with the same frequency. So the first one. The first part was correct. Then we calculate antinode positions for each pair of antennas with the same frequency. That's what we really needed to do. We go through the group of antennas of their positions. We check if the number of antennas is more than 2. If not, we just continue. Then for ion range now antennas, so we get 2 different antennas. We get their position. We calculate the antinode through the antenna 1 at distance 2. So antinode X, antinode Y. Distance between 2 antennas multiply by 2. The same for the y-axis. We calculate another antinode, then we add antinodes if they're within the grid bounds. Perfect. I like that. Yeah, this is definitely how I would like to approach this one. So yeah, we create a group of antennas, then we compare each two different antennas. We calculate the distance between those on by x and y, and then we try to place here and here and check if they're within the bounds. That's the correct approach. Yeah, perfect. I like this one. Let's just commit the first part. Input data for the 8, implement solution logic to calculate yeah, for the task like part 1. And now let's see what we got in the second part, which should be a more tricky one.
Watching over your shoulder as you work, one of the historians asks if you took the effects of resonant harmonics into your calculations. Whoops! After updating your model, it turns out that an antinode occurs at any grid position exactly in line with at least 2 antennas of the same frequency regardless of distance. This means that some of the new antinodes will occur at the position of each antenna unless that antenna is the only one of its frequency. So these 3 T frequency antennas now create many antinodes.
What? Antinode occurs at any grid position exactly in line with at least 2 antennas of the same frequency, regardless of the distance. Okay, so probably I see now. So it's like, you know, it's like a wave thing. We have those T's are antennas, and it happens that their frequency, like, are they positioned? Yeah, it's like the waves, but the frequency changes. Like if you're going to visualize that, the frequency would change depending on the placement of antennas. Could be. So like we have T and T here, and then we go and iterate through all of the grid and adding the same amount of distance, like the same distance. So like we have a wave, yeah, it's like a S thing, and then we add another wave, and then if the peaks intersect, we get this like a wavy how do you call it, trough. Yeah, we have peaks and troughs. If they peak, we get these antinode locations, like, as I understand that. But because it's a wave, it just continues. It just goes on forever. Therefore, we have repeated antinode locations. Yeah, it would be more interesting to visualize this one. As you see, but just on this picture, it is not clear whether the distance, like the antinode distance, will change. Yeah, I'm not sure. So in fact, 3T frequency antennas will exactly in line with 2 antennas are all exactly in line. So if there are also antinodes. This brings us total number of antinodes in above example to 9. 1, 2, 3, 4, 6, 7, 8, 9, or like exactly. So again, antenna occurs at any grid position exactly in line with at least two antennas of the same frequency. The original example has 34 antennodes. We have 0, 0 here, and then we continue, and then we continue here. Again, we have 0, 0, continue here, continue here probably. 0, 0, again, we go there, and continue. AA. Because AA are close to one another, we have the same distance, and just it will repeat the same pattern. So if they are close to each other, the antinodes will be on each like diagonal path. What else do we have? Why do we have an antinode there? Oh, alright, so probably it's A and A. No, it's not that. Probably this one, A and A. These antennas would produce us this antinode. So yeah, like if we would visualize the frequency as a wave, if we would visualize the waves there, the wavelength would be determined by the distance between the antennas. So it's a weird way. It's not really a physical thing, but yet interesting to see. So we get so the frequency is not determined by the number. If we would visualize that, the frequency or the wavelength won't be determined by the letter or the number, but by the distance between two of the antennas. Yeah, like that. What would I say? Yeah, I would like to we'll try because we already have this first part solved by GPT-4o O1 mini. We could get a correct approach, like a more correct approach from the smaller models. Let's try GPT-4o mini. So, calculate antinode positions updated. Group antennas by positions by their frequency. Same thing. Frequency antenna positions. Calculate antinode position for each frequency. It's just the same code as before. Check all positions in line with antenna. Okay, so now it goes for X in range, minimum of antenna 1, antenna 2, maximum of antenna 1, antenna 2. So it's for minimum of X between those and maximum of X. So from minimum to maximum plus 1, they add new position to X with the same Y coordinate. Not sure whether this is correct, but yeah, we'll see. 2, 1, 2, 5. 2, 1, 2, 5. It's too high. Okay, so yeah, GPT-4o mini wasn't able to iterate on the solution that it had before to improve it. Let's try 3.5 Haiku. Claude. What does it say here? It finds only one potential approach: modify existing, calculate and denote positions. You shouldn't really do that. You should have created a new function. Create a new function specifically for part 2 updated logic. Okay, so different approaches. It's not one. It will implement solution using approach 3, which will modify the existing. No, I would not like this one. But let's see what it suggests. So, check if antennas are in line. What does it mean in line? It was described in a task that they should be in line, but I don't see that's like any restrictions on this part when I was reading it. So, what do you mean in line? 2 dots. 2 like any dots on a 2D map, on any map, always will be in line. It's not like 3 dots in line. Yeah, because we had here, so for example, only 2 nodes that are in line. They have a distance 1, 2, 3, 1, 1, 2, 3, 1. So we have an antinode. That's why we had an antinode here. Again, 1, 2, 3, 1. Like 1, 1, 2, 3. Again, we have a antinode here. So what's not in line? Yeah. Let's try to run, and it gives us just 0. Okay, so no points for Claude 3.5 Haiku. It wasn't able to solve this one. Let's try Claude 3.5 Sonnet. Potential approaches. Use line equation to find all points between antennas. Use GCD to find all integer points on the line. Modify existing function to handle new requirements. Yeah, it created a new new function. It's better. And it placed all inside all functions inside of it. We have some GCD. Okay, so it's greatest common divisor. Now while B and B, A, percentage B, return A. So if this one is 0, it will exit. Get points online. Get all integer points online between 2 points. Calculate GCD. Find the smallest step. Get all points along the line. Let's see whether... Yeah, the answer is smaller for some reason. It doesn't have to be like that. What did we have previously? It's 2125. and the answer was too high. I'm not sure that the part 2 should have a smaller answer. This probably is incorrect. Yeah, it's too low. Okay. Sorry, bros. I need to go for 5 minutes. Just be here. I'm here. So, we continue, and I'm surprised that Claude 3.5 Sonnet didn't give us as the correct answer. I will not go through its solution, and I will revert it back. Check out. And let's see. By the way, we have O1 Mini inside cursor. As I understand, it goes inside the subscription that I have. So let's see. It should give us something. It's just thinking as the same thing as it gives us something. Okay, so we have existing code part 2, solve part 2, and then it's just doing something. The code is more readable probably. Let's see whether math is not defined. Why? It has an import. Was it applied though? I don't see. But okay. Yeah, for some reason import was late in the file. Okay, so now we definitely have a higher answer of 534, and it seems like it is more correct. 534. No, it's too low. It's still too low. 534. 534. Okay. So, again, O1 Mini didn't give us the correct solution. I would try this one more time inside my ChatGPT. I'm surprised that this problem is so difficult to implement with AI. Canonical line representation. Was this part like of the requirement just to confuse people, or I'm not getting? We to uniquely identify lines, avoid redundant computations. Yeah. So like, just to avoid redundant computations. Let's see. What do we have here? Yeah. Number is again bigger. Could be correct one. 934. 934. Alright, so from the second attempt, O1 Mini was able to solve this one. For some reason, it wasn't able to solve from the cursor. Not sure why is that. So inside ChatGPT, it was able to solve. Probably just second shot. Try it in another approach. Yeah. So let's figure out what the solution was. So we have frequency map, again, default dict. Then we append all the frequencies to the map, then process each frequency separately. If there are only one antenna of this frequency, we skip them. We have a set of lines that we have already seen. Iterate over unique pairs to determine lines. We go through all the cells. We get P1, P2 for position of the antennas. We try to get canonical line. Then, if this result is not in line seen, we add it to the set. Then we get from the line we get ABC, which are normalized, which are like which represent this equation: a multiplied by x plus b multiplied by y plus c constants, like, and the ABC are constants, equals to 0. And ABC are normalized, such as GDC of ABC equal to 1, and A is more than 0. I would really like to understand why did it do that. Seems like a correct way, but correct approach. But just why did it do that? So we get points on line A, B, C, width and height of the grid, probably, yes. And then we add antinodes. Again, it's a set, so we just don't repeat. Get points on line. How do you get the points on line? Given a line is a canonical, return all grid positions that lie on this line within the grid boundaries. Okay, I see now. So that's why we had to get this ABC, because we would get all the other points that lies on this line, by adding a distance probably. So if b is not 0, we go for x in range. So like a x, b, y are the multiplier of x, and b is multiplier for y. Like, probably not going to confuse anyone. So again, for x in range width, so we go through the width through all the points on x. Then we calculate y, which is minus a multiplied by x minus c divided by b. Okay, so we just solve this equation. We get we have this equation. We get, to get y, we need to move c on this side, a on this side, and then divide everything on that remained on this side by b. So we figure out what's the y position, and we check whether it's integer. I didn't know that float as method is integer. Nice way to check. So we convert it into integer if it's inside the grid we added to the point. Same for a. For x and y, we get, by the equation, we get x value, and then return the points. Interesting. Okay. Again, yeah, this does work. I like this approach, and I would like really to visualize the map with the frequencies. We'll just submit, because we've finished, where is it? We've finished our day 8. Congratulations, thank you for watching, but I'd like to visualize the map of the frequencies. Probably we'll use some colors. We will ask Claude to visualize this one. But firstly, let's try to figure out again what's the image is that they are producing. So again, we have a reindeer, we have a small Christmas tree, we have something, I'm not sure what's this one. But this one now starts to remind me of some picture, like if you place some picture on a wall, because we have different elements there, and we have this frame. This could be frame as well, or something. But yeah, we'll see when we get to the 25th day, what's the image, the full image of this one. Okay, now what we are going to do is to commit finish part 2. I won't be trying 01 now, because I don't have a lot of requests left. I won't be paying $200 for 01 Pro for unlimited requests. So yeah, 01 Mini solved it. Cool. I'm pretty surprised that Claude 3.5 Sonnet, which is on par with 01 model, sometimes even better than 01, wasn't be able to solve the both parts. Or is it? At least second part it wasn't able to solve. So 01 Mini, cool. I like that it was able to solve this one. Let's do create another composer. We'll not be using O1 Mini. We'll try Sonnet now. For visualizations, I like Claude. Let's ask it to create one. Hi Jarvis, let's create a visualization of the notes in part 2, like of the frequency. Let's draw something beautiful by using different colors. Right in a zip file. It will be using Matplotlib, NumPy. Yeah, generate distinct colors, visualize frequencies, collect antenna positions grouped by their frequency, figure, dark background colors, generate distinct colors, plot antennas and antinodes at each frequency. Should be fine. Let's run Python visualize. And wow, this is beautiful. Container folder. Wow, yay. So by star we have the antennas of different colors, and the circles are antinodes. Why did it connect? Okay, now I see. So we have two antennas, and we have an antenna there, antenna there, antenna there, there. How else would we visualize this one? If we would have a real waves, they will intersect not only at this point, but all around those. So it will create a circle. Therefore, what can we do? We can try to draw circles around those. So what should I do? What the visualize is doing? Where's the S? So where did it get the antinodes? Calculate and plot antinodes for range, plot, and antennas. Frequency map. Get points in line. So yeah, it's using and recalculating the solution once again, but let's use again GPT-4o, the O1 Mini, not GPT, O1 Mini. Now what I'd like to do is to draw actually a circle like thing. Instead of the line, we get a circle of antinodes. Hi Jarvis. Now the task is different slightly. Now we need not to find all the antinodes that are in line with the nodes, but we need to draw. Why did it stop? Hi Jarvis. We need to draw actually the waves, like a circle lines. We need to find all the antinodes that are around the circles and then repeating the same way they are doing with the nodes currently, but we need to find all the points that are around now. Not sure if this explanation is will be comprehensible for the AI, but let's see. Generating wavefronts. Yeah, this is what it's called. Circles. For each antenna, we will generate all possible wavefronts, circles with an integer radii. Okay. To efficiently generate the points on a circle, we'll use midpoint circle algorithm, which is commonly used in computer graphics to draw circles. Since we're working in a discrete grid, some points might not lie exactly on a mathematical circle, but will be approximated to the nearest grid points. An antinode is a grid point that appears on the wavefronts or two or more antennas of the same frequency. Yep. So, yeah, it has a name for it. Part 3. Perfect. It will be not existing part 3. And then let's visualize the part 3 instead with the wave fronts. If the yeah, just like that. For each antenna, generate a plot wavefront circles. Accept and let's visualize. Yeah, it takes slightly more time. Yeah, wavefront. Oh no. Doesn't look like a good representation. I don't see anything. They're the same color. Yeah. I don't see no wave fronts. Could be that the part 3 solution is not correct. It's not generating the actual wavefronts. More visible, increasing number of circles, adjusting their appearance. Why do you increase the number of circles? You shouldn't do any of that. Let's see if we get something else now. No, nothing changes. Why do you add? Wow. Alright, so now it has generated the actual wavefronts, but it's just too messy. I don't think that's the correct one. Why do you add more? You have the task only to generate the correct ones. Okay. Apply and run. Yeah, this is what I wanted. Wow. Let's open it. Okay. So, and let's try to figure out. So we have, for example, these blue ones. So what would be the circle? The antinode should be located over there. So like, I'm not sure. What does it do? And it's also, it's not a circle. It looks like a, could be a circle though. But it's more looks like an ellipse. I wonder if that's a correct location. So we have to. I'm not sure if the color is correctly represented. So like, it just generated a circle. Oh, they're different colors. Actually, I'm not sure that this is a correct one. It looks pleasing though. So we have green here, green probably here, and the circle goes like that. Yeah. Let's see other one. Blue and blue. Antinode should be located there, but nothing appears. Like, hi Jarvis. I'm not sure that this is a correct representation. We should find all of the antinodes and just the same way we should have drawn the other antinodes that are not in line but have the same radius from the antenna. So therefore, please draw these circles instead. It should also have it has the solution. Yeah, let's open it up with, wow. Again, I'm not sure that this is a correct, but it's definitely beautiful. So 1 circle, 2 circle, 3 circle. Just generated all of the circles around all the antennas. Alright. I like the gradient. So yeah, if we look at each point, we would find a circle around it at any antenna, I mean. So we see that this probably, yes, some are just covered, some are more visible. So we have a circle around there, or this one is more visible, circle, 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 circle. But the circles are all the same, like frequency. Yeah, the same distance always. And this is not what we wanted, but yeah, the image is pretty. Let's try once again. Hi Jarvis. Now actually you have generated a circles with the same distance between from all of the antennas, but what you should have done that yeah. Hi Jarvis. Is actually that you should have found all of the points like of the antinodes and then draw those circles, not this with the same frequency, but it would change depending on the distance between the antennas. So therefore you should draw this one instead, these circles instead. They will have a varied frequency, the varied distance of the circles. Let's see. We could give us this one, this task to the O1 Mini again. If Claude won't give us the correct solution. Again, something's happening with the API and just didn't generate anything. Okay. Yeah. Distinct colors, get distance, visualize wavefronts for antenna, max radius, circle points, get circle points. It could be that the solution of the part 3 is not correct. Therefore, the wavefronts are not, it's just not changing the solution. No, you should have changed the solution, not only the visualization. Let's run it if in case it is not correct. It takes some time again to visualize. Probably not correct answer. Part 3, solve an updated part puzzle. Circle wave. Each antinode forms wavefronts from two antennas meet. Okay, and then visualize. It takes just too much time. It's probably not the correct visualization. Accept and visualize. Again, it just takes too much time. No. Wavefront. No. I'm not sure that, yeah. Seems like it's doing something Incorrect. So let's do the same prompt to the GPT to 01 mini. Actually, generate the circle, same distance. Then I'll ask Claude to visualize. So let's copy the code and let's paste it here. Let's see if solution, yeah. Now the more nodes are then we'll ask the same thing. Create a visualization of nodes in part 3. Yeah. But it won't be a circle like we had before. It will be the actual node. Golden ratio, why? Generate distinct colors. Oh, wow, I see. So it's using golden ratio to what? Generate and visually distinct color with enhanced contrast. Enhanced saturation and value for better visibility on dark background. Okay, visualize, apply, accept, and run. Let's see what we have. Is it what's the name of the file? Frequency, wavefront. It's the same. Again, seems like where's the visualization? Visualize. Keep the rest of the code the same. What? What? Just go with the full code. It was. Oh, I see. No. It just didn't. It just doesn't know about the visualize file. So we'll delete everything in visualize, and we'll show it that it exists. And say yeah. Let's do it again. So let's see. Visualize antenna field. Frequency map. Okay, and it's not iterable. Plot wavefronts, max radius, circle, calculate and plot antinodes. Okay. Apply, accept, and draw. Antenna visualization. Why do you keep getting us mistakes? Yeah, accept. Later text, customize the plot. Calculate plots and antinodes. Scatter. Antenna visualization is ready. Firstly, it's not dark background. Yeah, total antinodes 200, 250, 500. Number frequency say 48 antinodes. What? So antinode will appear on every point, apparently. Okay. Let's do something else there. You know what? Let's not ask. So let's delete the visualize file, visualization, solution. Let's revert it back to the delete to the part 2 and start from scratch. Okay, so hi Jarvis. Let's visualize the wavefronts instead of the part 2, what we had only, where we had only the antinodes locations, but instead we need to visualize the wavefronts. So use the distance between the nodes in order to calculate not the location of the antinode, but the radius of the needed wavefront, and it should repeat with the same radius, increasing the difference should increase. So we should get a visualization on a dark background with the wavefronts, which are actually representing was representing by the radius dependent on the antinode position and distance between the nodes. So draw these circles. So what we're going to do now is not to actually determine which points on the grid will be the wavefront, because currently we just get all the points. If we're trying to like interpolate, not interpolate, but we're trying to map the points of the wavefront onto the map, onto the grid, and because there are not so many points, they are just using all of the available points on the grid. But I would like to just draw a circle for all of the for the wavefront, not to show the antinode. Visualize wavefronts. The background. Wow. Is it like you can apply style? Okay. Okay, let's see. Solution. Part 2 and visualized wavefronts. Wow, yeah, that's what I wanted. Yeah, this is definitely much better. We don't see the color of the antenna, though. We'd like to have the same color. Hi, Jarvis. Hi, Jarvis. Make the color, make the antennas as a star with a color of some. Why do you stop? Hi, Jarvis. With some color, with some determined color, and then the wavefront should have the same color as the antenna. And we need to specify the same color for the frequencies. And solution. And let's see what we got. The resolution is not quite what I like, but yeah. There are two yellow ones. Then the wavefront is only that. Why? So yeah, 1, 2. There should be a bigger one. 1, 2, and somewhere the wavefront should be their distance, like 1, and should appear somewhere over there, but I don't see it. It's a nice picture, but I'm not sure that this is correct one. But so again, two orange ones, orange. Do we have a larger circle? Yeah, we have one. Hmm. Because there are too many lines. How can we make this more visible? Hi Jarvis. Can you make the DPI bigger so that there's a higher resolution, and also make the lines of the circles more thin that we can see actually like the differences? DPI. Not TPI, it's DPI. Except it doubled the figure size, increased the DPI, reduced the circle line width, reduced the circle alpha transparency, made the grid more subtle. What? 73 megabytes. Yeah, this is it. This is it. Takes too much time. Please. Alright. Alright. Can I make it just slightly? Why do you do that? I need it just slightly. Slightly smaller. Okay. How do we navigate? Okay. So we have, for example, we need to find closer. Yeah, so green. This distance is this one, but what it does, it only creates two circles intersecting with one another, and that's it. That's not the correct one. So what we should have had is a circle, one over there, like distance between them. The point will be there, so the circle should go around this point, and then should repeat. Then the same for this one. Circle should be like here and around which point? Probably around the center of the stars. Yeah, is it? Is it? Let's go back. So we have, yeah. So the circle center should be in the middle of two antennas. Let's change this. Hi Jarvis. Actually, you should have created a circles that go and repeats itself, and the center point should be in the middle between two antennas, and the radius should be the same as calculated for the antinode part. But the picture is fine. Like, not fine, it's just pretty. It's just not correct. So again, we should have a point of the intersecting, like a middle point between antennas. And then we should have a circle that goes, yeah, it should have, it should be, no, it's not this point. So this distance we copy like here. Forget it. Let's see. Let's draw. Distinct colors. Collect antenna positions. Assign colors to frequencies. Plot antennas and wavefronts. Calculate midpoints between antennas. Calculate the distance between antennas. Radius should be the same as the internode distance. Not really. This was my mistake. The radius should be like the radius, the distance between the center point and the anti-node location. Let's have it change, but let's see. It's even bigger now. It's 115 megabytes. Oh wow. That's really nice. It could be correct. Hey, it could be correct. It's not correct, but it's pretty close to what I wanted. So it show that the radius, the distance between those became the radius of the node. So that's why we have two antennas enclosed in a circle, but the circle should be bigger. The distance between the node, like the antenna, and the outer part of the wavefront should be the same as the distance between two antennas. I like the picture much more. Yeah, let's see. Let's close this one. It takes really long time to visualize. I wonder what would be the file size. Yeah, okay. It's even bigger, but let's see. Yeah. This is it. Wow. So if we were to compare, so we have two red stars, two antennas. The distance is that, and that we have a distance between them repeated, and we have this wave front. Yeah, and we should have a repeated one in the same distance, somewhere over there, but I don't see it. Okay, so let's do that. Again, we have a yellow one, and it should repeat somewhere over there, but it didn't. So it just drew one. But probably that's the problem, that it just, we won't see anything if they will be repeated. But is it? So, this seems repeating, but probably not. We have one circle, probably second circle, is it? And there are also like dashed lines and dotted lines. Could be that the dotted line is repeated, like we have this one, and then probably somewhere around this we should have another dotted line. What was the solution? Visualize wavefronts. Calculate midpoints between calculate internode positions. Only one position. Probably calculate distance between midpoint and internode. Correct radius to the wavefront. Draw a circle. And this is a dashed line. Then draw additional circles with increasing radii to show repetition, but now it's a dotted style for other circles. And also decreasing alpha for outer circles. So yeah, it was probably doing that, but let's decrease the line width and decrease it here. And what else? Yeah, just decrease the line width. Yeah, it's now smaller. It's less visible though. And the stars are too big. You know what? Let's make stars. I'll just ask it. Let's make the stars smaller. Oh no, I'll faster do it myself. So again, line width. Let's keep it the same. Alpha should be around 5. Let's make it 8. Line width should be the same. Let's make 6. Fill false. The star is marker size. Let's make it like 5. Marker edge width. Let's make it 4. And let's draw it again. Wow. And let's see if that's one is correct. So we have a wavefront for those. And then again, I just don't... it's really easy to miss it. The wavefront. The wavefront should be like somewhere there. Is it? Yeah. Seems like it. 1, 2, 3. The second one is there. Again. What was it? 1, 2, 3, 4. Yeah. Yeah, this one is correct. Wow. I like the result. Yep. Thank you for watching. And this is what we have. Took too long to generate this, but it was worth it. Yes, 167 megabytes for this image. I won't be committing it, but I would like to move the visualization to the zip file. Oh crap. I've deleted it. Can I? Yeah, whew. Frequency visualization. What? No, it was not this one. Okay. Accept all and print what solution and visualize. Apply. Accept. Python visualize. What? Why so fast? Why was it so fast? Visualize. No. Why? What's happening? Action visualize wavefront data. Let's make it use the same input, so it would work. Okay, if only if we run the solution file, visualize, and we need to remove the visualize from this one. Okay, so yeah, wavefronts. Let's see if The visualization is correct. Containing folder. Yeah, this one is correct. I'm just not committing it to the GitHub repo. Yeah, everything except. Okay, so except wavefronts. Solution. No. Why would you do that? Stage changes. Solution. Yeah. Just revert it. Visualize. Yeah. Yeah, move reading. Implement wavefront visualization logic. Okay, now. And git ignore png for now. Okay. Yep. Thank you for watching. This is what we got. And see you the next day.